And I wrote down in red the equation that is the original equation, but then I did some stuff to it, which makes it look like this new equation here. Can you list some transformations for me, please? What transformations do you think would belong to this case? Help me out here, folks. Transformations. What transformations? Give me a few transformations that you think would apply in this case. Hello out there. Anybody? Anybody? Who is that? Hand is going for somebody. So, Janaya, please go ahead. Mm-hmm. No, I'm not changing it. I'm saying the original function. In fact, we're going to use y equals 3x as the first set of points that you would put the original points from the original equation before all these transformations took place. So for instance, I'm going to use the following values of x: 0, 1, and 2. I'll just use those for now. So if these are my x values, then what would 3 to the power of x be? Well, 3 to the power of 0, remember, is 1. 3 to the power of 1 is 3, and 3 to the power of 2 is 9. Okay? All right, so I'm seeing finally some answers here. Horizontal stretch by a factor of 2. Very good. So let me write that out. Let me get some of the stuff out of the way here. Okay, so HS by a factor of 2. Hopefully everybody sees why that is. If anybody's not sure, then you need to ask. Vertical translation down by 9. Absolutely. VT down 9. I see a horizontal compression by a factor of 3. Okay, that one I'm not going to agree with that one. I'll tell you why. If the original function is 3 to the power of x, then this 3 is just simply part of the original function. All of the stuff that you're trying to get the transformations of are taking place with the exponent and that number on the end. Okay? Don't understand why it's a horizontal stretch by a factor of 2. Okay. Let me just answer some questions from before that. Okay, so Caleb, do you see why I'm saying that there is no horizontal compression here? Right? The compression would come from anything in front of the x, right in front of the x. And the only thing in front of the x is the half. Okay, so let me get to why it's by a factor of 2 for the horizontal stretch. And right in front of the x is that half. You see that half there, Ava? Right in front of the x. It's in a bracket, so it's been factored out already. Right? Do you see that, Ava? That horizontal, do you see where the half I'm talking about? Okay, perfect. That would be where you get the horizontal stretch from. And you always do 1 over that for horizontal. Horizontal is kind of backwards. I keep saying that. So you always do 1 over that number. So 1 over a half is 2. Do you see what I'm saying, Ava? 1 over a half is 2. If I take 1 and divide it by a half, I get 2. So therefore, that's why there's a horizontal stretch by a factor of 2. All right? I think it was Noah who gave us the vertical translation. I think everybody understands that. Vertical translation down by 9. What else is going on? I saw something else, and I think maybe Jeremy might have put that in already. There is one other thing that is going on. The left by 2, correct. So there's a horizontal translation to the left by 2. HT left by 2. Okay? And that's because of the x plus 2. Remember, horizontal is backwards. Just think of horizontal always as being backwards. Okay, let's get to the asymptote now. Now you're probably wondering, well, the last time it was whatever made the log 0. Well, it's not the same thing this time. The asymptote actually comes from, first of all, I want to make sure we understand this. When you have an exponential function, the asymptote is not vertical anymore. The asymptote is actually now horizontal. And it's very easy to get that horizontal asymptote. It's whatever the vertical translation is, but it's now going to be a y equals. So y equals minus 9 is my horizontal asymptote. Okay, so there's an HA. Let me put that under here. It's not a VA, it's an HA. All right. By the way, let me just confirm. Can everybody still see what I'm writing on the board? Yes, Jeremy, go ahead. Okay. Mm-hmm. Correct. For which one? For the exponential ones? For logs? Oh, for logs. It's whatever. Well, it's not so much what the no. What it is whatever makes the log zero. So set whatever you take in the log of and set that equal to zero. Mhm. No, there aren't. And in fact, I'll just show you very quickly. I'm just going to do a quick diagram on here. Right? This is just a very rough diagram. Here's what a log function looks like. It looks, and I'm going to put it in a different color. So let me use where's my palette now? Okay. Oh, I didn't mean that. It's now snowing. That was not intended. I hit the wrong button for that one. All right. So just enjoy the snow for another couple of seconds. And let me try and find my little palette thing now. Where is the little palette thing? Where is it? Where is it? Oh, there it is. Okay. So let me go to blue, right? So what I'm going to do is I'm going to show you what a typical log function looks like. A typical log function looks like this, right? Hopefully everybody can see my graph. That graph, it's going forever down and forever up, right? So FYI, a log function, the range of the log function is YER, because it's always going to continue going down. It's always going to continue going up. There is no restriction on the range of a log function, okay? There is a restriction on the domain because, as you can see in this graph, for a log function, because of this vertical asymptote here, it's mean that this function will never go to the left of that vertical asymptote. So it means that has to be greater than zero. But we know that. You can't take the log of a negative number. Okay? So there's what we're saying about that. Now, if you're looking at an exponential function, I'm going to put a different color for that. I'll put that as a, I don't know, I put that as a I don't know, green line, right? Dark green line. An exponential function looks something more like this, right? Now, this does have a restriction on the range because it doesn't go down below that horizontal asymptote, but it doesn't have a restriction on the domain. It goes forever to the left and forever to the right. Okay? Okay, Nicholas. By the way, are the transformations x's the transformed x is 2x minus, so we're going to get to that in just a minute. Yes, we're going to get to that in just a minute. I just want to make sure everybody's clear on what these graphs look like. So this one, the green line, hopefully you can see my green line. It's not very green, but anyway, let's just pretend that it is green. That green line has a horizontal axis, so that's the exponential. I just labeled it exponential. So that's exponential. Whereas the blue line, right? That one is a log function. This one is a log function. Oh, it's still green. Oh, geez. All right. Anyway, that's the log function. And that one has a vertical asymptote. Do you see what I'm saying here, Jeremy? Does that make sense? Jeremy, are you there? Mm-hmm. Correct, correct. If you look at the graph, you can kind of see that. It's going down and then it starts to go into this treading towards the asymptote. So it doesn't go any lower than the asymptote, right? Or it doesn't go higher than the asymptote, depending on whether it's been flipped or not. And on the other hand, for the log function, it's an unrestricted range, but a restricted domain. Okay? All right. We just looked at the horizontal translation, sorry, the vertical translation. What that vertical translation does is it drops the exponential function down or raises it up. So that's what happened. That horizontal asymptote, which used to be at the y equals 0 line, that's now wherever this thing has been dropped to, that becomes, or raised to, that becomes the new horizontal asymptote. Okay, you're welcome. Okay, so Noah was asking now about what happens to the transformed x's. So let's get to that. Let's get to that. So we're going to take those x's, the x's, we're focusing on the x's now, we'll get to the y's later on. And we are going to, yes, multiply each x value by 2 because it has been stretched by a factor of 2. So that's what we're going to multiply by 2. And then it says left 2. So then we're going to subtract 2 from it, which is exactly what Noah says. So let's do that for the first x value. So 2 times 0 is, of course, still 0. Then minus 2 would give us minus 2. So there's our first x value transformed, right? Multiply 2 by the next value. 2 times 1 is, of course, 2 minus 2, which would give us 0. 2 times 2 gives us 4. 4 minus 2 would give us 2. Does everybody see how I got those three values? Is everybody clear on that? Because I can go over it again if you need me to. Folks, I have no issue with that. Joel says yes. Okay. Is everybody else clear on that? Could you go over it again? I sure can, Isaac. So what I'm saying is, because of the horizontal stretched by a factor of 2, horizontal refers to the x values. Remember, Isaac? And horizontal translation left by 2. I'm going to take each x value, multiply it by 2. It's been stretched. So multiply it by 2. And then I'm going to subtract 2 because it's been shifted to the left by 2. Does that make sense, Isaac? Right? So I took each x value. 2 times 0 is still 0. Then minus 2 gives me minus 2. 2 times 1 is 2. Minus 2 is now 0. 2 times 2 is 4. You're welcome. And then minus 2 would be 2. Okay, for the y's now, what's happening? There's only one thing going on with the y's, the vertical translation, right? It's a vertical translation down. Good, Nicholas. It's a vertical translation down by 9. What happens to each of my y's there? Tell me what happens to each of my y's. You just subtract. You said x is actually y minus 9. Yeah. So each y, you're going to take 9 from it. So the first one is going to be minus 8. The second one is, remember, you're taking 9 from it, so it's minus 6. And the last one is going to be 0. Okay? All right, so those are my points. Now we can go further because we're going to get x and y intercept. The truth is, we have those answers already, right? We have the answers for that from the table. Can you see from the table? Sorry, how did you get the initial x and y values? Okay, Kristen, thanks for the question. So for the x values, I just simply put in values of x. I just put 0, 1, 2, 0, 1, and 2. I just chose values that were easy to work with. And then I said the original function before all of the transformations took place was the y equals 3 to the power of x. That's the original function before the transformations, Kristen. Before we started doing shifts and stretches and all this other stuff, we just had 3 to the power of x. Does that make sense so far? Okay, so then I just simply took each of these x values and raised 3 to that number. 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. Okay, all right, great. And then I did all of the transformations and I got these new values. Now, you can tell from the table what the x and y intercepts are. Who can tell me right now, before we do the we're gonna do the calculation, but before we do the calculation, who can tell me right now what the x-intercept is? Just looking at the table, what's the x-intercept? Anybody? Well done, it's 2, right? I'll just put that on the side right here because we already know what that is. We're going to work it out algebraically as well. How about the y-intercept? Does the table tell us what the y-intercept is? It does. It's minus 6. So I can put that in as well. But let's see if we can actually work this out. If we didn't have it in the table didn't give us that information, could we have worked this out for ourselves? Now, how does one get an x-intercept again? Can anybody help me out with that? How do I get an x-intercept again? Set y to 0. Okay, so we'll do that. So if you just scroll on the page to where I am right now, so 0 is equal to, because remember I'm setting y to 0, 3 to the power of a half x plus 2. Let me erase this thing on top here. Actually, it's getting in the way. And then minus 9. So what I'm going to do is I'm going to put that 9 on the right side. That would make sense, wouldn't it? I'm going to put that 9 on the right side. Is equal to 3 to the power of a half x plus 2. No, we actually haven't done anything like this before, solving an exponential equation. But let's see if we can think this through. Can anybody see a way that I might be able to solve this exponential equation? I have 3 on one side, I have 9 on the other. Can anybody think of a way that I can perhaps solve this without using logs? I know some of you are going to take it, make both sides have a base of 3. That's a great idea. So I'm going to make the 9 become, what would 9 be as a base of 3 then, Jeremy? Everybody else, not just Jeremy. What would 9 be as a base of 3? 3 to the power of what? 3 to the power of 2, okay. Is equal to 3 to the power of a half x plus 2. Okay, well done, Jeremy. What would that suggest to everybody in the class, not just Jeremy now, right? If I have 3 to the power of 2 is equal to 3 to the power of a half x plus 2, what does that suggest my next step could be, right? They're both the same base on both sides. Cancel out the 3's. I think you're right. So what we're going to say, so what would your next line say then if that's the case? Right? Cancel the bases. So what would I say on my next line in order to solve this then? Tell me exactly. So therefore the 2, good, is equal to the half x plus 2. All right. Let's keep going. Thank you, Isaac. Thank you, Harish. What am I going to do to the 2 sides now to solve this? What's a good way for us to solve this? Just regular, ordinary equation style, like what we did back in grade 9. What can I do on the 2 sides now to get that x on its own? That's what I'm trying to figure. Multiply both sides by 2. That's a good idea, actually. So let's multiply this whole side by 2 and also this whole side by 2. Well, this side just becomes 4. That 2 and that half cancel out, so I'm going to be left with x plus 2. And of course, that's easy to solve. That means that x is equal to 2. But we knew that from our table, that x was in fact equal to 2. The x-intercept was 2. But how do we get the minus 6 now? Let's see now. Let's set our x to 0 this time. Okay? Everybody still following along on their board, hopefully? Everybody on, hopefully you're on page 5 with me and everything looks pretty clear, hopefully. Right? Let me get some feedback from you. Can you all follow along with what we're doing here? Shiobon says yes. Joel says yes. How about everybody else, folks? Perfect. Okay, so I'm going to go to the other side now. This time I'm going to say that my y-intercept is equal to the 3 to the power of a half times 0 plus 2 minus 9. Okay, okay. So that means that y is equal to 3 to the power of a half of 2. All right, 0 plus 2 is just 2, minus 9. So that's equal to 3 to the power of a half of 2 is 1, minus 9. And of course, 3 to the power of 1 is 3, so that would be 3 minus 9, which is minus 6. Again, we knew that from before. I'm going to go to my next page now, and I'm going to ask you to come along with me to number 6, and I'm going to put this all together in a nice, smooth exponential function, not a log function this time, but an exponential function. All right, so let me go to page 6 now, and I'm going to first of all, which should be my graph, I'm going to first of all put in my horizontal asymptote. All right, so let's see now. Let me come over to my toolbox on the right hand side over here. Select line, and then I'm going to change it to dotted, which is this little toggle here for dotted. I'm going to put in my line. All right, that's not the best looking line in the world. I'll be the first person to admit that. But folks, there's my line. Maybe I should change it to red. Yeah, you know what? Let me take that out and make it red because that will stand out a little better. So I'm going to change that to red. Okay, so let's try that again. So it's at 9. That's a little better. A little bit better. Okay, so there's my horizontal asymptote. What page is this on? I'm on page 6. Try page 6, Kayla. And let me know that you can see it. I just put my, in fact, what I'm going to do, one more thing. I'm going to make that bigger. So it's a little brighter. It's a little, yeah, I'm going to change it again. All right. I'm going to make it so that my dotted line is a little sharper. Okay. So here we go one more time. Last time. There we go. That's a much better looking horizontal asymptote. Page 6 was my question. I can't see the graph. Page 6 was, okay, so try the next page then. So I'm not sure why not. I really don't know why not. By the way, will the quiz be on the whiteboard? No, it's not. It's on D2L, which I haven't made visible yet. You see it now. Okay. It was weird. Okay. So here's my asymptote, horizontal, way down at -9. I'm going to I'm going to go back and see what my other features were from the table. So from the table, I knew it was -2, -8. I'm going to put that point on. -2, -8 would be right. Oh, let me change this back to the pointer now. So -2, -8 would be somewhere around here. And I also had the 0, -6, and 2, 0. 0, -6, and 2, 0. 0, -6 is here, and 2, 0 is here. So I'm thinking I have a pretty good, I'm going to zoom out a bit so I can easily draw my graph. I think I have a pretty good idea what this graph is going to look like. I just zoomed out so I could do it. And folks, here comes my graph. Not going to be great, but it's going to be my graph. I'm going to come up through here, up through here. Ah! Oh, it's dotted still. Oh, let me change that. I don't want it to be dotted anymore. Let me take off the dotted. And here we go. That's actually not that bad. As graphs go. I kind of missed the 2 there a bit, but and I'm patting myself on my back. I probably shouldn't do that, but mine wasn't too bad. I probably changed a little bit right about the whole thing left. I didn't mean the whole thing to go. I'll try one more time though. All right, a little better, not much, a little better. All right.